If the laws of physics don't care which way time goes, then why do you? Why can you remember yesterday but not tomorrow? Why does a dropped glass shatter, but the shards never leap up and politely reassemble themselves on the table? If the equations allow it, what's stopping the movie of the universe from running backward? That's the puzzle. And it's a good one, because it makes you suspicious of something you probably never questioned before. You think time flows forward because that's what it does. But that's not an explanation. That's just describing the problem with confidence. So let's try something else. Let's slow down and ask a more careful question. Not, why does time move forward, but what do we actually mean when we say it does? Because the moment you try to define it, things start to get slippery. You look at a clock, the hands move clockwise, and you say, aha, that's time. But the clock is just a machine. It's doing what the laws of physics tell it to do. And here's the funny thing. Almost all of those laws work just as well backward as forward. Take a simple case. A ball rolling across the floor and slowing down. Run that film backward. The ball speeds up and rolls back to where it started. The equations don't complain. They don't shout, hey, that's illegal. They're perfectly happy. Even collisions between atoms work that way. Reverse all the velocities, and the math still holds. Physics, at its deepest level, is remarkably indifferent to the direction of time. And yet, your life isn't. You don't unspill coffee. You don't unburn toast. You don't wake up knowing what you'll have for dinner tonight, but forgetting what you ate this morning. Something is clearly asymmetric, and it's not coming from the basic rules of motion. So where is it coming from? Now, before we go charging into big words, let's do what we always should do in physics. Let's try to build some intuition. Let's play with a picture in our heads. Suppose you walk into a room and see a deck of cards neatly stacked on a table, all ordered, all tidy. Now suppose you walk into another room and see the same deck scattered across the floor, cards everywhere, some face up, some face down, corners bent, a mess. You don't need to think very hard to know which situation is more likely to have happened naturally. You never think, oh look, the cards randomly jumped into a perfect stack. You assume the neat stack required effort. Someone had to do something special. The messy state, on the other hand, feels inevitable. That feeling is important. That's not philosophy. That's physics whispering to you in everyday language. Here's the strange part. The messy arrangement is not more chaotic because the laws of motion prefer chaos. They don't. It's messier because there are vastly more ways for the cards to be messy than for them to be neat. One neat stack. Astronomically many messy configurations. If you jiggle the system blindly, randomness doesn't aim for disorder. It simply explores possibilities, and most of the possibilities look messy to us. Now hold on to that idea, because we're going to stretch it until it explains why time seems to have a direction. Imagine a box divided into two halves, left and right. In the beginning, all the gas molecules are trapped on the left side. Then you open a little door. The molecules start flying around, bouncing off the walls, and soon they're spread evenly throughout the box. You've seen this experiment, or at least you've been told about it. It's boring, predictable, gas spreads out. But ask yourself something carefully. Is there anything in the laws of motion that forbids all the molecules from later happening to gather back on the left side? No, nothing forbids it. It's not illegal. It's just ridiculously unlikely. The number of microscopic arrangements corresponding to evenly spread is so overwhelmingly larger than the number corresponding to all on one side that you will wait longer than the age of the universe to see it happen by chance. And here's the key insight. The gas spreading out didn't require a new force or a new law. It required statistics, counting, probability. That's it. Now, suppose you film the gas spreading and play it backward. You'd see the molecules mysteriously organizing themselves, flowing neatly back into the left side. And you'd laugh. You'd say, That's impossible. But you'd be wrong. It's not impossible. It's just fantastically improbable. So already something interesting has happened. We've found a way to distinguish past from future, not by changing the laws of physics, but by talking about what is likely versus what is unlikely. Time's arrow, as people like to call it, isn't etched into the equations. It's hiding in the statistics. At this point, people usually say a word, and that word is entropy. And unfortunately, the moment that word appears, many brains shut down. So let's be careful. Let's earn the word before we use it. Entropy is often described as disorder, which is not wrong, but it's not very helpful. A better way to think of entropy is this. It's a measure of how many microscopic arrangements correspond to what you see macroscopically. That's a mouthful, but the idea is simple. If what you see can be made in many invisible ways, entropy is high. If it can only be made in a few special ways, entropy is low. A neatly stacked deck of cards is low entropy. A scattered deck is high entropy. Gas confined to one side of a box is low entropy. Gas spread everywhere is high entropy. Now here's the punchline, and it's subtle. The second law of thermodynamics doesn't say that entropy must increase because nature likes disorder. It says that if you start in a low entropy state and let the system evolve naturally, it will almost certainly move toward higher entropy simply because there are more ways to be there. That almost certainly is doing a lot of work. The law is not absolute in the way Newton's laws are. It's statistical. It's overwhelmingly reliable, but not logically unavoidable. And that distinction matters because it explains why time feels directional without smuggling in a mystical force pushing it forward. Now, let's ground this in something closer to home. Your bedroom. You clean it. Everything has a place. Clothes folded. Desk clear. That's a low entropy state. Now you live your life for a week. You don't try to make a mess. You're not deliberately chaotic. You're just existing. And somehow the room becomes disordered again. Why? Because there are many more ways to be messy than tidy. Every small action you take explores the space of possibilities, and most of those possibilities don't line up with your carefully imposed order. To maintain low entropy, you must continuously input energy and information. You must fight statistics. This is not because the universe hates you. It's because probability doesn't care. Now comes a very common misunderstanding, and it's worth hitting it gently but firmly. People say, if entropy always increases, how can living things become more organized? After all, you're more structured than the soup you eat. Cities are more organized than the rocks they're built from. Doesn't that violate the second law? No, because the second law applies to closed systems, and you are not closed. You are an entropy exporting machine. You maintain order locally by increasing disorder elsewhere. You take in low entropy energy from the sun and dump higher entropy energy back into space. The total entropy still goes up. You're not cheating. You're paying the bill. So entropy isn't about everything becoming uniformly messy. It's about the balance sheet of possibilities. Now let's circle back to time. Why does entropy increase toward what we call the future and not toward the past? Why don't we see entropy decreasing when we look backward? The uncomfortable answer is that we put it there at the beginning. The universe appears to have started in an extraordinarily low entropy state. That's not a philosophical claim. It's an empirical one. The early universe was hot, dense, and remarkably smooth. And that smoothness corresponds to very low entropy for gravity, which is a whole story by itself. But the essential point is this. The universe began in a special state. From that special beginning, entropy had only one statistically likely direction to go, up, and once you accept that, everything else falls into place. Memory works because recording information requires increasing entropy elsewhere. You remember the past because the physical process of memory formation aligns with the direction of entropy increase. You don't remember the future because there are no physical records of it yet. records of traces left behind by entropy-increasing processes. This is why broken glasses don't unbreak. The unbroken glass corresponds to a vastly smaller set of microscopic arrangements than the broken one. To reverse the process, you'd need to coordinate an enormous number of particles with exquisite precision. The laws allow it, but the odds are laughable. Now let's test this understanding by changing the scenery. Suppose you're watching a video of billiard balls colliding on a table. No friction, no sound, just balls bouncing. You play the video forward, then you play it backward. Can you tell which is which? Probably not. The motion looks equally plausible both ways. Now add friction, add sound, add heat. Suddenly you can tell the balls slow down. Energy dissipates into tiny, invisible motions. Entropy increases. The backward version now looks absurd. Sound waves converge into a sharp clack and jump back into organized motion? No, that doesn't happen. What changed was not the fundamental laws, but the number of degrees of freedom involved. Once energy spreads into many microscopic forms, coordinating it back is statistically impossible. This gives us a powerful test. If you're unsure which way time is flowing in a process, ask yourself, where is entropy increasing? Where is information being lost into microscopic detail? That direction is what you call forward. Now, let's deal with another subtle confusion. People often think entropy is about ignorance, about what we don't know. There's a grain of truth there, but it's dangerous. Entropy is not merely subjective. It's not just in your head. It's about how many microstates correspond to a macrostate, regardless of whether you personally know them. Even a perfect being with complete knowledge of every particle would still agree that there are more ways for gas to be spread out than confined. Entropy is about counting possibilities, not about human confusion. And this leads to a final, slightly unsettling thought. If the arrow of time comes from a low entropy beginning, then time's direction is not enforced locally, it's inherited globally. We live in a universe that remembers its past because it started in a state that made forgetting the future inevitable. That's not comforting. It means the deepest reason you can't unspill milk is tied to the initial condition of the cosmos. But physics is not in the business of comfort. It's in the business of telling you how things actually work. So here's the real lesson, the one worth carrying with you. Time doesn't flow forward because the laws demand it. It flows forward because the universe started in a special state, and probability's been doing the rest of the work ever since. Entropy is not a force. It's a bookkeeping rule, a brutally honest accountant, keeping track of how many ways things can be. If you want to check whether you really understand this, try a simple exercise. Pick any irreversible process in your life: cooking an egg, aging a photograph, charging and discharging a battery, and ask yourself very carefully, where are the microscopic details going? Where is the information spreading out? If you can answer that, you're not just repeating words. You're thinking like a physicist. And that's the point. Not to memorize entropy, but to see time not as a mysterious river pulling you along, but as a statistical story, written one improbable beginning at a time.